So thank you all for coming to my talk. My name is Andrew Case. So I'm the Director of Research at Volatility and also one of the core volatility developers. So I've been involved with volatility since about 2010 and working on it very heavily since then. So I'm very excited to give you this talk today. This talk has two purposes. One is to introduce you to Volatility 3 and some of its very cutting edge features. But what I didn't want to do is just show you how to run a plugin and what some basic output looks like, things that we've been talking about for 15 years now. What I really wanted to focus on is what I would consider interesting and modern forms of code injection. So the types of code injection, the way to get code into a victim process that isn't something that was in our book from 2014, isn't something that's going to get picked up by an EDR right away. So during this talk, you'll get to see a lot of cool new Volatility 3 plugins. Unless you're tracking our GitHub tracker of like every single commit, these plugins are brand new. And so you'll get to see a lot of new plugins and you'll get to see it against a lot of interesting malware. If you're not familiar with Volatility 3, this is a complete rewrite of the Volatility framework. So it's not like we took Volatility 2, ported it to Python 3, bolted on a few things. This was starting from the first line of code, everything brand new. Volatility was introduced at Black Hat 2007. So you can imagine since then we've learned a lot about how to write a better framework, make it more scalable, make it easier to use, and also to meet the needs of investigations better. If you look back at investigations from, say, 2010, maybe you were doing them yourself, systems literally had 512 megs of RAM, a gig of RAM. And so to take that versus the machines we investigate now, you need a totally different framework when you have 128 gigs of RAM. We have a client at Volatility who has machines with 2 terabytes of RAM that we very often analyze. And Volatility 2 by default isn't going to do much with that besides just break, right? So we need to have new ways of analyzing memory to be able to deal with these new systems. And then being scalable is also important as well. Again, going back to 2010, 2011, a large scale investigation, quote unquote, was like 5 machines, where now we have 100 machines, 1,000 machines. In an automated fashion, we want to find the ones that are compromised, have signs of malware, so we can just pivot to those key systems. And then the other big thing, by being in this talk, you are seeing features that will, like I said, some of these were put in Volatility like literally last week. It is very much new features being added. But in sometime in April 2025, so if you follow us on any social media or LinkedIn, whatever it might be, there will be a full cutover. The Volatility 2 repository will go read-only. We will ignore any issues or questions about it. And Volatility 3 will be the stable framework. It is going through an immense amount of testing right now. Literally, as I'm speaking, it's being run across 700-800 memory samples, being compared against what we know are good artifact sets, making sure the output is stable. So you're getting an introduction here to what will be the main framework not too long from now. If you're not familiar with memory forensics, if you haven't used it before, the reason we care about it so much, the reason I've spent like 15 years now on it, lots of nights and weekends and everything else, is when we deal with what I would consider modern attacks. So at Volatility, where we're investigating networks where a very motivated nation state or criminal group is targeting an organization very specifically. In the types of places we work, sometimes it's individuals that are targeted very specifically inside of an organization. And when you look at malware that's used during those attacks, it is memory only. And when I say memory only, I'm not talking about fileless malware. When memory only means the malware is in memory, so it's in the memory space of a process or the kernel, if you reboot the machine, that malware goes away and it doesn't come back. Versus fileless malware, which is mostly a marketing term that I hate, that is where malware writes itself to like the registry or a link file, something like that. You can turn that machine off, do disk forensics on it, and you can find the malware that is not memory-only malware. So when I say memory-only malware, what we're talking about today is malware, again, if you reboot the machine, it's gone forever. So obviously you have to do memory forensics to find it. And the interesting frameworks, the ones we see in the wild, are truly memory only. And one of my favorite reports of all time, and it's not a Volatility report, it's Microsoft. You can see the citation at the bottom, is they found this company out of, I think it was Australia. So it was like a hacker for hire group out of Australia, had a very sophisticated tool set, and Microsoft just completely put them out of business. If you haven't read this report before, it is amazing. So they went through every feature that the malware had, every capability it had, and just burned it to the ground. Like that stuff will never work again undetected. But what I have here is one little snippet from the report. Microsoft called the main part of the framework core lump for reasons they describe in their report. And what I've highlighted in red is they're talking about how the actual part of the framework that hits the victim machines, it is memory only. So it does not touch disk at all. You have to do memory forensics. And if you look at the capabilities, it can do key logging, it can capture screenshots, it can exfiltrate files and allow attackers to run commands remotely. So all the things the attackers want without a single trace on disk. And then what's great is we've obviously preached memory forensics a long time, starting with SolarWinds, which I think we all heard of. CISA started publishing their emergency directives. This is where they tell agencies how they have to respond to a certain incident. And starting with SolarWinds and every emergency directive after that, the very first thing they say is you have to do memory forensics. Because with SolarWinds, and then there was an attack about a month later that we detected at Volatility, where Exchange servers were being compromised across the internet. So you could just send data to the Exchange server. All the payloads, the exploit, all the payloads that came after were memory only. And so CISA at this point, every other government agency that publishes these types of reports, the very first thing they say is do memory forensics or you're out of luck. Because the rest of the report has all the IOCs you're supposed to look for, but those IOCs are only in memory. So if you get a disk image, what's the point? The IOCs you're looking for are not there. So our group's motivation, we have our research team at Volatility. We like to deep dive as low as possible into malware in different related areas. Our motivation for what we're talking about today is we knew we were working on Volatility 3. We didn't want to just re-implement all the techniques from Volatility 2 because we know they don't work on modern malware. It's kind of the point, right? This malware is written to bypass all the old techniques. So we wanted to write new plugins, update old plugins to catch all the new forms of code injection. But before we can start detecting crazy malware in memory, we need to understand what does code actually look like in memory and how does the operating system track it. On Windows, the way that the memory ranges of a process are tracked are called virtual address descriptors, which everyone calls VADs because that's a long and annoying term to say. So with the VAD, for every region inside of a process, it's going to tell you where that range starts and ends. It's going to tell you the protections, which we'll see on the next slide, are very important. And then if that memory range maps a file, it's going to tell you that as well. So this is the vadinfo plugin. This is essentially straight from Volatility 2, but this is one of the most powerful sort of stepping stone plugins that you need to detect malware. And there's a couple things from this slide that you need to remember, or what I'm going to talk about later isn't going to make much sense. I have it highlighted in red, but you can see we're in the same process. So this service host process, PID 732. For every memory range, you get the starting address, ending address. The important parts here, if you look on row 2, where I've highlighted the page execute write copy, and then you can see in this case that's mapping kernel32.dll. One of the main things we're going to key in on when we start detecting malware is if you use the legitimate APIs. So a DLL gets loaded into a process legitimately, how you would expect the OS to do it. There's two things that are going to be true. One is the protection is going to be page execute write copy, which is highlighted in red. And then second, there should be a file associated with it. Because if you're mapping a file, if you have code coming from a file, kind of makes sense there should be a file there. Versus if you look on the third line where you can see there's not a file mapped, it's page read write, okay, that's fine, like your variables and such can be there. But if you're expecting code to be in a region, like I said, it has to be execute write copy and it has to map a file. So remember that rule because it's going to be very important as we go through the talk. Oh, the second important thing here is this data comes out of the kernel. So we're going to see that malware takes significant efforts to do anti-forensics. It tries to change a bunch of data inside of its own process's memory, data that it can actually access. And that's actually good for us because we have plugins that just look for those changes and it tells us the malware is there. But the VADs can be considered a source of truth. The VADs are in the kernel. There is no research ever to where you can manipulate the VADs such that volatility won't find it and the machine will stay stable. We've had a lot of people, it's fun for us, people try to break volatility and stuff, right? People would try to like mess with the VADs and we would test their proof of concept, and then like 30 seconds later, the machine blue screens. That's obviously not very useful in a real attack. So the VADs are a solid, stable source of information that we can use out of the kernel to compare to what process memory is telling us. So that's the second key takeaway off this slide. Versus when we look in process memory, we're going to see that we have lists of the libraries that were loaded. If you have a DLL that's legitimately loaded into a process, that's going to come from a DLL like load library or load library EX, and that's going to do a couple things. So if you legitimately load a DLL, the important thing here is in process memory, that DLL is going to be stored in 3 lists. And then you can imagine, as like an antivirus or an EDR or a tool like Volatility, we should be able to consult those lists and find the DLLs that are loaded. So the takeaway here is if you have code that is legitimately loaded, you're just using a DLL, that's a totally normal operation to do, that DLL should, 1, have a VAD that is page execute write copy and has the file path, and then 2nd, it should be in these lists in user land. So the other thing that's really helpful is when DLLs get put inside of these lists, there's a data structure that tracks this, and that data structure also has the load times. So if you haven't seen this before or you're not using it, I put the slides in because you 100% should be using these in your investigations. So starting with Windows 7, so Windows 10, 11, the server versions, when a DLL legitimately loads into a process, there is a timestamp associated with that inside of the DLL data structure. So what we do, and as part of our automated processing at Volatility, is we say, okay, if you have especially your critical processes, your services.exe, your LSASS, things like that, we say if a DLL loads into that process more than 5 minutes after the process starts, that is something we flag on. Does that make sense? Because a process should start, its DLL should load, and then if you see DLLs after the fact, like why are DLLs randomly showing up in critical processes? So like I said, that's part of our automated flow. So what you're seeing here is an example of why that's so helpful. We're running the DLL list plugin. So for every process, it's examining those lists that I was talking about, the 3 lists in process memory that hold all the DLLs. And as you can see, we have our LSASS.exe. In the second row, you can see the timestamp of that umpdc.dll. That was November 10th at 21:05:04. That is when that process started. But then you can see about almost exactly an hour later at 22:06, we have debug help loading. If you know what debug help is, that's part of the APIs to inject code, and it's also going to help with stealing credentials. So this would automatically fire on the stuff we use at Volatility and tell us, hey, a DLL is loaded into LSASS more than 5 minutes after it started. That's something we should key in on. But I will admit that doing it this way is annoying. If you have 1,000 samples, you don't want to run DLL list and so on. So in Volatility, we made timelining much easier. Has anyone done timelining in Volatility 2? Did anyone enjoy it? It was horrible. As a Volatility developer, I will admit it was rough. Remember, Volatility 2 was written a long time ago, had a lot of stuff hacked on along the way, and timelining was one of them. So timelining, you consider it like a first-class feature in Volatility 3. If you're a programmer, basically it's as easy as you can take any plugin that otherwise just like prints timestamps to the terminal, you implement, you inherit from the timelining class, and then you implement a function called generate timeline, and that's it. Now your plugin shows up in every timeline that's generated. And unlike Volatility 2, where you had to run like 6 plugins and hope you ran them in the right order, and then you glue the output together, there's just, you see in the first line, there is just one plugin called Timeliner. You say -- create body file, you feed that through MacTime, and you're done, and that's it. Life is so much easier, and you can use your timelines out of memory. Related to what we were seeing on the last slide, you'll see where I have it highlighted in red. The first one I have highlighted red is that debug help loading at 16:06:17. And literally within the same second, and I didn't cut the output or anything, 2 lines later, at the same second, we have an MFT entry for LSASS.dump, which is the default file name, well, really the force file name for a number of methods to access credentials and write them out to disk, or at least get a process memory dump of LSASS. So in this case, this is why it's so powerful, right? Like when we see the DLL loaded, we look at the timeline and we say, okay, did anything else weird happen within that time frame? In this case, like I said, the exact second that we get extra DLLs loading, we also have a process dump of LSASS. It's a dead giveaway. So with all that in mind, malware wants to avoid all this, right? They don't want their DLLs and everything to show up in memory. So there's a couple things they could do. This slide is a quick refresh, would be your traditional injection artifacts. The reason I wanted to talk about it, to spend 2 slides on it, is because it tells you all the stuff malware is going to do after the fact to be a little bit more stealthy. With the traditional ways of injecting code, you would, on the left, the remote DLL injection. This is where you would force your victim process to load a DLL of your choosing, which is great, I guess, because now you have your DLL loaded and that DLL can do whatever it wants. But we just showed over the last couple slides how that is super loud to memory forensics. This is exactly what causes those time discrepancies that we automatically key in on. So the first one on the left is not stealthy at all. It populates the DLL list. The DLL list plugin shows it to you. It's in the timeline and all the rest. So another way that malware would try to do this is they would just inject shellcode into a process. But this is also not remotely stealthy at all, because you have to set up a memory region. It has to have code in it. That memory region is not mapping a file, and it's definitely not execute write copy. So this is something that we're going to flag on right away. So what this looks like, if you use malfind in Volatility 2, we have basically an improved version of it in Volatility 3. This is it detecting shellcode, so that what was on the previous slide, it's saying, hey, there's a memory region that's page execute read write, and at the beginning of it is a shellcode block. This is definitely malicious. So again, super loud way of injecting code, which is why I call it one of the more traditional ways. To get around this, malware, this is still used a lot, even though it's old. Reflective DLL injection is where we still want to inject a DLL in memory. Writing a sophisticated payload in shellcode is pretty miserable. And we also want to avoid those DLL lists. So this is a memory-only way of doing things. Normally, that DLL will be downloaded over the internet in encrypted form, decrypted in memory, and then loaded memory only. So we don't have a DLL on disk. We're not calling load library. And then those data structures in process memory don't get populated. So this is incredibly loud to memory forensics as well, because basically you have a VAD that is mapping an executable, but there's nothing in the DLL list for it. So malfind is going to pick up on this right away and say, hey, this memory region, it doesn't map a file. It's not execute write copy, it's execute read write, and there is a PE file at the beginning of it. So we pick that up right away. This is just a funny example of Emotet. Maybe you had the not fun time of dealing with this in your environment or a customer's environment. If you look at how this runs with the command line plugin, the command line is absolutely crazy, right? Like, look at the DLL name that's running through run DLL. It's like randomly generated directory. The thing doesn't even end with .dll. It's out of someone's app data local folder. So if you had something to process command lines, maybe this would fire. If you saw it yourself, it would definitely fire. But this malware is also just super loud in general. It does reflective DLL injection, which malfind picks up on right away. Plus, it also injects shellcode that we pick up on right away. So even if the command line wasn't so crazy looking like it does now, malfind would pick up on it easily. So you can imagine malware authors did not want to get caught by something like malfind or the techniques it's doing. EDRs can, to a certain extent, do the same thing malfind's doing, depending on how they're operating. So this is where we get to process hollowing, and this is where things start to get new and interesting. The idea with process hollowing is, let's just look at a slide. It has evolved over time. We're going to look at many, many examples over the next couple of slides. The original form of process hollowing was saying, hey, I don't want to inject a DLL into a remote process, and I don't want to inject shellcode into a victim process. because of all the reasons I just talked about. It's super loud, memory forensics finds it in one plugin run. So instead, what I'm going to do is I am going to spawn, or let's say create, a process that is legitimate on the machine. So I'm gonna pick something like LSASS or Explorer or like a service host where there's 100 of them running anyway. I'm gonna start one of those processes, but I'm gonna start it in what's known as a suspended state. And in the suspended state, what that means is basically the process gets half set up. So there's an address space for that process. And then inside of that memory space, the executable itself gets mapped, and NTDLL gets mapped, and maybe kernel 32 gets mapped, and that's it. So the operating system sets up like this half-created process, and then gives control back to whatever process is the one creating it, like the parent process that's controlling it. So then with process hollowing, what we're going to do in this initial form is we're going to get rid of the original executable. So in this case, we're going to unmap LSASS out of memory, and we're going to write our own malicious executable back on top of it. So that's why it's called hollowing, because you have a legitimate looking process. If you look in Task Manager or sysinternals, it's going to say LSASS is running. The path on disk to the executable is going to be LSASS. But what is actually in memory and running is whatever malicious executable we wrote over where LSASS used to be. So this is looking at it manually. So before we use a plugin that's going to figure this out for us, we're running PS lists. So we're getting the list of processes on this machine, and we can see that there's 3 LSASs running. So the goal would be Windows should only have 1 LSASS process running by default. So we want to figure out which 2 are the malicious ones. So if we dig around by hand a little bit, we can figure out that at the address with the 1000 hex, so let me see here. So this address with the 1000 hex, this is where the process executable should be inside of those processes. And then we're filtering. So this is a new feature of Volatility 3. Instead of having to grep and like do insane greps and multiple greps or awks, you can use the filters feature to just automatically filter on any of the columns. So we're saying show us only rows where the start VPN column, so the starting address, matches this. And then you can see we only have 3 lines of output. I didn't cut the slide or anything. That's just the filters working. So then what we can see is in one of the processes, we have page execute read write, and it's mapping a file. In 2 of the other LSASs, which we know 2 of them have to be malicious, at where the process executable should be, first off, there's no file, and the permissions are page execute read write. So this is 100% process hollowing because we wrote our malicious process over. But again, no one wants to do that over like 1,000 memory samples. Let's just automate it. So there was a plugin. It's like 9 years old now, but it's still really cool. So we do a volatility plugin contest every year. People submit plugins. Whoever wins, we give them a bunch of money and like free spots in our trainings and things. And if today is the first time you've heard of process hollowing, go read this blog post. I was talking to some people before. I work with a bunch of college students. If they're going to do malware at all as like their research or their master's, the first thing I say is go read this blog post. It's 9 years old. It's still incredible. It's very long. It's basically where the author at the time, 2016, went through every process hollowing technique. He goes instruction by instruction in Ollie debug, showing you how it works, goes through every API, everything. So if you haven't seen process hollowing in action, that blog post will always be very helpful. So he wrote the plugin at the time that automated basically all the techniques he was showing in the blog post. So what we wanted to do is, obviously 2016 is 9 years ago now, there's new forms of process hollowing. We took his work he did at the time, plus all the updated detections that we had worked on, and we have a new plugin called hollowprocesses. So what you saw 2 slides ago, where there was 3 LSASs and like 2 of them weren't mapping right, that was Stuxnet. We have so many slides on Stuxnet, it will always stay in our presentations to start. So what we see is we're running windows.hollowprocesses, and if you look what's in red, it's automatically telling us what's wrong. So the first line says, hey, for PID 868, the VAD that's hosting the process executable, so there's a thing called in kernel memory for every process, there's this thing called the section base address that tells you where the main executable should be mapped. And the plugin saying, hey, where the main executable should be mapped, the permissions are page execute read write like we saw, And then this thing that says non-file backed region, that's Volatility's way of saying this thing's not mapping a file. So we already know with 100% certainty when we see this output that there's process hollowing. And then if you notice in the same exact PID, it's saying, hey, we walked the DLL list. So the first output that I just talked through, that comes from the VADs. So then what Volatility also does is it walks those DLL lists and it makes sure that for every DLL, one, it's mapping a file. In this case, it's mapping a file, that's fine. But then it says, hey, this LSASS.exe that's mapped at this address, the permissions for that VAD, the one hosting it, are page execute read write, also 100% a sign of malware. Now you technically could have done this with Volatility too, but you have to run like 5 plugins and glue a bunch of stuff together. It's not something you could really scale out. So versus more modern malware, this is the hollowprocess plugin versus a fairly recent Cobalt Strike version. It's always hard to talk about Cobalt Strike because it changes every 3 minutes and like the versions change and people configure it different. But this is something that's pretty stable. So you can see Cobalt Strike is inside of a service host process, and it looks similar to what we saw for Stuxnet. It says where the process executable should be. First off, there's no file there. That doesn't make sense. And then second, the protections page execute read write. Remember, it should be execute write copy. What's really weird about Cobalt Strike is it seemingly fakes DLL list data structures. So it has a hollowed region, which normally you would think like isn't in the DLL list, but then it has where it added the service host record inside of the DLL list, but it's still pointing back to that region that's page execute read write. So even though it maybe like fooled AV or something, it just made itself louder to memory forensics, and now we get extra lines of output telling us that this machine is definitely compromised. And then the other thing I wanted to point out is there's malware. If you noticed this slide and this slide, it's a bunch of like page execute read write. There's malware that tries to be stealthy and slick and says, I am not going to make my memory allocations executable. When I set up these memory regions, I'm not going to do page execute read write because that's super loud. Instead, I'm going to do something like page read write or page read only and then change it after the fact. As you can probably expect, and the fact that there's output on the slide, Volatility doesn't care about that. We're going to detect the malware anyway. So in this case, actually, I wasn't 100% sure on where this malware was, so I don't want to name it because this came from an actual case. So this was Windows hollow processing, the Volatility 3 hollow process plugin versus process hollowing malware, but you can see there's nothing execute read write. The plugin saying, hey, there's a DLL in the list. Here's the path. It's at this address. The permissions are not correct. It's not page execute read write. Sorry, it's not page execute write copy. It's page read write, 100% malware. The OS would never do that. Now, the other thing, another trick that process hollowing malware likes to do is change the image base address, which is supposedly super stealthy, but it's awesome because it's 3 lines of code in Volatility and you catch the hollowing technique. So in this case, this is against, I found an open source sample that did this because I couldn't find something from a real case that I could sanitize enough or was like comfortable sanitizing. So this technique gets used by real malware, but there's a GitHub link for an open source form of it. So what this malware does, I mentioned before, inside a kernel memory for every process, there's this thing called the section base address that tells you where that executable should start. And then in user land, related to the data structures that are tracking the DLLs, there is a data structure that says, like in user land, where it expects the executable to be. So in this form of process hollowing, what the malware does is instead of all that work of like unmapping the original executable and writing over it, all that stuff, the malware injects its own executable and then simply changes the image base address to point to itself. So remember, the process is initially suspended. It's not running yet. So the malware can put its own code in, change the image base address, and then when that process gets awoke again, when it comes back to life, the image base address is going to point to the malware, and that's where code's going to start executing. So it's actually pretty stealthy from like a live system, but like I said, it's super loud to memory forensics. So this is the same hollow process plugin. It's saying, hey, the image base address reported from the PEB. The PEB is the name of the data structure in userland. The one in userland is saying it's 7FF63F2D versus the one in the kernel that cannot be manipulated by malware. So what the operating system actually set up, the section base address, it says that pointer or that number should be 7FF, 6DB32, and so on. So this is something that malware cannot beat. Like, it cannot bypass this check, and it completely just burns this form of process hollowing. Now, in the second line is also something that's really interesting. So what you can do is there's a form of process hollowing where, if you remember in the visualization slide I had before with Stuxnet, it would unmap the LSASS executable and then write itself right back on top of it. What some malware does is it will unmap, let's stay with LSASS. So we're hollowing LSASS, we're gonna unmap that executable, but the malware will write its payload somewhere else. And so in this case, the plugin's giving us extra information, which is like, hey, the section base address is saying the main executable should be at this address, but in the VADs, there's not even a region there, which means the malware just completely unmapped the application executable. Again, Windows never does that. This is 100% a sign of malware. So the hollow process plugin's pretty awesome, right? At this point, if malware tries to tamper with the VADs versus what the DLLs think, it's either going to get caught by malfind or hollowprocesses or both. If it tampers with the DLL data structures entirely, there's a plugin from Volatility 2 that we ported over called loader modules. Just to save time, I didn't want to go through that because the plugin's old. But that will sanity check just the DLL data structures, and then that tells you about it as well. So at this point, any type of like DLL injection, shellcode injection will automatically be detected. So what can malware do at this point if it still wants to inject code? There's two popular things. One is it can overwrite its own header, and then the other one is it can try to fake execute write copy, but as you'll see, this is just super loud to volatility as well. So we'll go technical for just one slide. So let's say you wanted to allocate a memory region in your victim process that is page execute write copy, because then volatility is going to say, hey, this is a legitimate region, I'm not going to flag you, and the plugin's not going to produce any output. Well, to start, the main APIs you're going to use for that are either virtual alloc or virtual alloc EX. The reason you do that is because they have a parameter called FL protect, which is where you get to pick the permissions. You get to say, hey, allocate a memory region for me in either my process or a remote process, like the victim process, and give it these permissions. And you have all those permissions on the right, all the defines that say which permissions you can give. And if you notice, one of them is page execute write copy. But what sucks for the malware authors, if you can see it highlighted right at the bottom, is page execute write copy is not supported by these functions. So you can allocate memory regions in a remote process with everything but execute write copy, so that is not going to work, and the malware authors are out of luck. So this is great. This is actually amazing for us with volatility. A lot of things would fall apart if malware could abuse this API to actually do execute write copy, but the kernel doesn't let you do it. So it makes everything super loud in our detection plugins. So what if you still want to get execute write copy in a VAD of your choosing? So it takes way too long to explain, but Windows has these things called sections where you can set up a memory region in your process, so like the malicious malware process, and then basically copy those memory regions into your victim process, and Windows does all the hard work for you. Using the APIs to do that, map view of section, create section, and so on, you can actually specify a VAD as page execute write copy, and then basically clone it into your victim. But this is incredibly loud, and like 4 different volatility plugins detect it, because you're making a memory region that doesn't make any sense. Because now your memory region's execute write copy, but one, there's no way through this API to associate a file with it. So it's like I have a memory region that should be mapping a file and there's no file. Okay, 3 different plugins are going to catch that. And then second, all you did was make an execute write copy VAD, but the DLL lists are not updated. So now LDR modules and the other ones are going to detect it as well. So you're basically out of luck. Now, the one thing that does kind of work by default is overriding the PE headers. So with volatility, when we're going through the VADs, if we want to know if a region's mapping potentially like an injected DLL or something like that, we look at the first couple bytes and say, does this look like a PE file? Well, what a lot of malware does is after it loads, it just overwrites all of its header, which is the bytes we're looking at. Once an executable is loaded, the header is never referenced again, so it's totally fine to overwrite your header. If you have a rootkit in kernel memory, it can do the same thing. But luckily for us, we have threads. And threads tell us exactly where code is executing. And so by overwriting the PE header and then running code in there, that is a direct sign to volatility of like, this is memory only malware, this is injected code, go investigate it. So to start, this is what the threads plugin looks like in Volatility 3. It is much more useful than the one in Volatility 2. So threads are kind of annoying. So they have 2 start addresses. I'm just going to say start address as a singular one, or it would make some complicated ways of explaining it. But every thread has two starting addresses. And depending on how you call the API, you're going to populate at least one of them. But basically what that means is when that thread, so that unit of execution, the thing that's telling the OS where to actually execute code inside of that process, when you make a thread, you have to say what address to start executing at. And then, like I said, that can populate one or potentially both of the start addresses inside the data structure. So you can see here we have our threads plugin, and for every thread, it's saying, here's the DLL it maps to, or if it doesn't map to a file, then we don't have a file there, which probably shouldn't be the case. Maybe that's malware. And then this is, it lets us look at it. The problem with this, of course, is on a real memory sample, this plugin produces thousands of lines of output. You don't want to look at that by hand. So instead, we just want a plugin that does all the hard work for us, which is our new Suspicious Threads plugin. This is another plugin where there was no equivalent in Volatility 2. So for a thread to be considered suspicious, the idea is we're going to take both of those starting addresses for every thread. So those are addresses where code should live or where the operating system is running code, which means if we like basically cross-reference that address with the VADs, the VAD that's pointing to should be backed by a file. So if it's not backed by a file, it's suspicious. The VAD should be page execute write copy because it's hosting code. If it's not, that's suspicious. And then the other thing we do is we take that section base address pointer that tells us where the executable should be. And if there's a thread pointing to a file that ends in .exe, that's not the main one, we call that out as well. Because there are process hollowing techniques where they basically let the main, say like the LSASS, just live in memory, but it doesn't let it execute. And then it maps in a totally different .exe file into that address space, which again, super stealthy on the live machine, but incredibly loud to volatility. And then also if a thread is suspended, like the main process thread is suspended, that doesn't make any sense. That is another way to catch process hollowing. So we call that out as well. So I separated the output here. These are actually from a couple different malware samples rather than having like 5 slides with 1 line each. The first 3 here, again, this is showing why we think the thread is suspicious. So it's saying, hey, in this Chrome process, there is a VAD that has a non-backed file region. So it's a VAD that's not mapping a file, but there's a thread pointing into it. So that doesn't make any sense. And then the protection for it is page no access. So this is my favorite type of malware. And people do talks at conferences with their open source tools that supposedly bypass memory forensics. So what they'll do is they'll set up VADs that are page no access. So you think like, I can't even read the memory that's there. You can't do anything with something that's no access. So that initial protection is no access. They go back after the fact with virtual protect and they make it all executable. But again, it's just super loud to volatility. It's a dead giveaway. So the first 3 are basically saying, hey, these 3 different processes have threads pointing into memory regions that aren't backed by a file. And even if there was a file there, the permissions are all wrong. No access, execute, read, write. Again, it should be execute, write, copy. And then on the bottom 2, the south.exe and the DLL host, this is the other form of it. So you can fake, like I said, you could do your map view of section and say, hey, this memory region's execute, write, copy, but no one cares because it's not backed by a file anyway. So Suspicious Threads calls it out instantly. And then I'll reference this at the end because this is from like the DEF CON talk I did a couple months ago. There are, like I said, code injection techniques that will use suspended threads and basically never allow the main application to run again. That makes absolutely no sense. So you can guess what the plugin does. It walks every process gets the state of the main thread. And if it's suspended, it prints it out because that's going to be malware. And so this is finding the dirty vanity technique, which was used to bypass EDRs and so on, but again, super loud to volatility. The last sort of thing I'll talk about is process ghosting and transaction tampering. So this is super cool. There was a lot of work in the last 1-2 years on this. Again, allow it to memory forensics, but from a technical perspective, is super interesting. So I would recommend like reading all the resources on it. So the idea here is malware doesn't want to create VADs and threads and all these things because, as we just talked about, Volatility is going to detect it right away. So what they want to do is get it where they literally just run a malicious executable. So you have an executable on disk that is 100% malicious. It can even be mimikatz in a lot of demos, and they still get it to run. Defender, your different EDRs don't find it because of the ghosting and the transaction tampering. There's two forms of this. One is they basically abuse NTFS transactions to make it where when a process is starting, the OS thinks it's one executable, but it's actually a totally different executable. So then your antivirus will scan like notepad.exe and say this is clean, but the executable that's actually running, like I said, is 100% like malicious malware that is on disk, but the AV and the EDRs are redirected somewhere else in their scanning. So that's one form of it. The other thing is, the other form of this is the malware will get executables to run, but they're marked as deleted. And quite honestly, this is hilarious because you'll have a process running. The OS thinks the file is deleted, which doesn't make a lot of sense because it's a process that's running. So if your antivirus or your EDR or sysinternals or whatever else that you use tries to open a handle to that file, which is a prerequisite to read its content, you have to get a handle and then like read on that handle. The OS is like, the operating system is like, hey, that file is deleted, you don't get a handle and you can't read it, even though the operating system is gladly running it as a process. So like I said, reading the resources on this are super interesting because it's all these weird gimmicks to basically bypass the OS. But it led to some really fun research and a new plugin called Windows.process ghosting. And the idea here is, this is the detection flow. So we walk all the processes. If the file object, which the file object is just the data structure that says, here's the file that's executing. If that file object is unset, because that's a side effect we noticed of, there's like, this slide is like 15 different techniques that we made memory samples before, and they all got caught with these three things. We didn't need like 15 different checks. So one of the side effects is you look at the file object for the process and you're like, hey, this process isn't running from a file, which doesn't make a whole lot of sense. So let's call that out. Then what we do is walk all the memory ranges of the process, similar to like malfind and the other ones we talk about do. And we say, if this VAD, if this memory range is mapping a file that's an executable, so like a .exe or a DLL, and the file object is set as deleted, that's bad also because that doesn't make any sense. And then the last one is for that same file object as we're walking through the memory ranges, if it's marked as delete on close, which is basically like, hey, when this handle goes away, when the process terminates, delete the file, that doesn't make a lot of sense either, so let's call it out. And in all seriousness, this was super fun research writing this plugin. So this is against a technique called transacted hollowing. So combines all the things. It's process hollowing that is abusing NTFS transactions. The implementation is super cool. I have the GitHub repo linked for it. But you can see our process ghosting plugin. What it's able to do is it's like, hey, there's a process that calls itself calc.exe, but it's actually running from the temp directory, and the name is like th7.temp. It's a randomly generated name. And if you look, the file object is 0, which again means like, hey, a process is running not from a file. That doesn't make sense. And the delete pending bit is set, which is going to make it where the OS can't scan it. And this is super cool. This is where, like I said, if your EDR is like, gets the notification that a process is starting, so your EDR or AV is like, hey, I got to scan this to see if it's malicious, it's literally going to scan calc.exe, the normal calculator under system32, but the process is running from that .temp file, which is mimikatz, and literally mimikatz in this case. So everything's wrong here, and then so the plugin's going to call that out. This is versus process ghosting. We catch this two ways. One is the first line of output's like, hey, the process is running, it doesn't have a file object. Okay, that doesn't make sense. The second line is where we walk the VADs, and it's like, okay, where the main, again, that section base address that tells you where the executable should be. It's like, hey, the section base address, its file object isn't there, and that entire memory range and file is marked delete pending. So we catch this technique twice in the same plugin. And then this is our everyone's best friend, Cobalt Strike. So we have our beacon process. It has a file object, so it didn't mess with that. It is not delete pending, but it sets up the process and the handle with delete on close. So if you try to kill that process and then go get it from disk or anything of that nature, you like to do disk forensics for some reason, you want to close that process, go scrape the file off the file system, it will automatically be deleted when the process terminates, which is super loud in memory, which is why Volatility instantly finds it. So those are all the new plugins and all the ways we catch all the malware we see in the wild. Hopefully you found the talk interesting. If you haven't seen Volatility 3, it's on GitHub. Like I said, it's fully open source. Also, if you found this talk interesting and all the resources, I did a talk at DEF CON that is on YouTube. It was one of the it was like 4 of us for months researching every EDR bypass technique that's used in the wild. As you can guess, we wrote a bunch of Volatility plugins to detect it. It led to a 20-page white paper with IDA screenshots and every technical detail you could ever want. And DEF CON records the talks, and so that's the link to the talk. So between the stuff here and the resources and the DEF CON talk, you were very well caught up on all the crazy malware that's out there currently. And that's the references if you want them. Thank you for attending, and I have a couple minutes for questions.
So if you unmap LSASS from a process, does that make the operating system unstable?
No, so all you're doing is it's actually really interesting. So all you're doing is unmapping the memory range that's hosting like that LSASS executable, but then you map in your own like whatever malicious code you want, and you set up like the image-based address or do one of the thread tricks so that when the process comes out of the suspended state and actually starts running, it's pointing to the malicious code. The reason it's so powerful if you're not doing memory forensics is, say you have like a sysinternals or you have like some people have like their live forensics tools that call the APIs and like, you know, sends them out to some system for processing. All of those APIs are going to tell you it's LSASS. It's going to say the executables system32 LSASS.exe. Everything is going to say LSASS, but what's in memory is actually whatever malware got injected there. So that's why I have to do memory forensics to say like, hey, this looks like LSASS, but it's not actually LSASS. There's this weird region. But that's why it's so powerful. It's because like LSASS is kind of weird because there should only be one, but that service host is like 100 on every machine. So most malware will process hollow service hosts because would you actually notice one more service host running? No one would, right? And the OS, like any tool that like runs on the live machine to then like do analytics or send it off to a processing server is just going to tell you another service host is running when actually the malware is fully active on the machine. So,
thank you.
Yeah. Our plugins are not looking for specific file names or strings or addresses. It's not like a YAR rule. We're looking at the system state, which means we're generically saying, hey, for all the memory ranges mapping an exe file or a DLL, they should be page execute write copy. They should map a file. And then separately in those DLL lists, there should be a record of it that matches it, because that's what the OS is going to do. So any code injection technique, new or old, that violates that, the plugin's going to find it. And quite honestly, like we have a huge, I was saying how we have like Volatility 3 running all those samples. We have several hundred infected samples in our test set. And it's actually fun because we write a plugin and run it, and a sample that we had for 3 years had malware that we didn't know about because now we have some new way to generically detect it. And so we're looking for violations in system state. So same thing with threads, right? Like we say, hey, for a thread, those two start addresses should point into where code is, right? It should point into a region with a file. That memory region should be page execute, read, write, all those things. Those are invariants that if you have just benign code and the OS is doing its thing, those are always going to be true. Where with malware, you start to violate those invariants and now you're like, hey, this is definitely wrong. And it's the same thing with the new stuff, the ghosting, right? You shouldn't have process executables running that are deleted, or they're going to get deleted when the process terminates. And so we're generically saying, hey, this is something in the system state that violates the normal OS way of doing things. You should look into it.
Great questions. Great questions. All right, everybody. Thank you, Andrew, for your fascinating presentation. And if you have any other questions, you can follow up with them